Light is the most familiar stranger in our universe. We see it every day, yet its true nature refuses to settle into one description. It arrives as a particle with a definite location only when we try to catch it. But when we look away, it spreads like a smooth wave of possibility through the fabric of space. Light behaves as if it lives two lives at once. Physics has spent more than a century trying to understand which life is the real one. Imagine a single photon, one tiny packet of energy. Release it toward a blank wall. But between the photon's source and the wall, we place two narrow openings side by side. Common sense says the photon must choose one opening or the other. There is no third option. That is how we expect objects to behave. Yet what appears on the wall is not a single dot as a classical particle would produce. Instead, we see a pattern of bright and dark stripes, the signature of a wave. It is a map of where the photon was more likely or less likely to arrive. A single photon makes a single dot when detected, but after sending many of them one at a time, the striped pattern slowly emerges. Each photon acts like a localized particle when it lands, but it travels like a wave with many possible paths along the way. We can block one opening and the pattern disappears. Restore both and the stripes return. It is as if each photon explores both paths at the same time, then interferes with itself. But that idea clashes with everything we know about experience. How can one thing go two places at once? Scientists describe this not with a physical wave of light, but with a wave function. The wave function does not carry energy through space like the ripples of a pond. It is a mathematical recipe for predicting the chances of different measurement outcomes. Where the wave function is large, the photon is more likely to be found. Where it is small, the photon is unlikely to appear. The wave function is a tool for guessing what could happen, yet it behaves with eerie precision as if possibility were somehow more real than matter itself. Then comes the strangest part. When we place a detector near one of the openings to check which path the photon takes, the interference pattern disappears instantly. Now it behaves like a particle choosing a single path. Once we learn which way it went, the mystery ends. The photon no longer explores alternatives. The very act of measurement seems to force a decision. This shift from many possibilities to one definite outcome is called wave function collapse. What causes the collapse? The mathematics of quantum mechanics predicts how the wave function evolves smoothly through time. It never includes a command that says, collapse now. Yet collapse clearly happens. We see concrete locations, we record results, we never detect shadows of the alternative histories that the wave function once allowed. The rules of quantum theory describe possibility in exquisite detail, but they remain silent about how a possibility becomes a fact. Some interpretations say collapse is not a real physical change. The wave function only reflects our knowledge. When we learn something new, the wave function updates to match. There is nothing physical about collapse, except our information catching up with reality. Others argue collapse is a genuine event. Something in nature eliminates unchosen paths and leaves only what we observe. If collapse is real, then it must be triggered by something. But what? This question becomes even more troubling with light. Photons have no rest mass. They travel at the maximum speed allowed by space. They cannot hold still even for a moment. They seem too simple to hide secrets, but they do. They interfere like waves until we look too closely. Then they act as particles that follow one route. Something in the universe decides when choices are possibilities and when choices are outcomes. Physicists have looked for the trigger in every corner they can think of. It might be interaction with the environment, a photon bumping into air molecules or scattering from dust. It might be the measuring device itself. It might even be consciousness, though that idea quickly collapses under its own lack of evidence. And there is another possibility that has drawn deep attention from some of our greatest scientific minds. Perhaps the deciding factor is gravity. Gravity is everywhere. Every piece of energy in the cosmos, including light, warps the shape of space-time. Maybe the wave function can stretch across many paths only when space-time is nearly flat. Maybe a superposition of different paths means a superposition of slightly different gravitational fields. Perhaps nature cannot tolerate space-time being in many states at once. If that were true, then collapse would not be a mysterious rule bolted onto quantum mechanics. It would be a consequence of gravity itself. The curvature of the universe would choose which possibilities become real. The boundary between the quantum world and the world of experience would be written into the geometry of existence. We are left standing in the glow of a single photon. Possibility stretches ahead of it. The universe whispers in every direction. But at some point, the photon must decide which whisper becomes its path. The search for who makes that decision is not simply a scientific puzzle. It is a question about the moment where reality chooses its story. Light reveals everything. Yet when we ask what light really is, we find the question shining back at us unanswered. Light moves through space as if it refuses to be owned by any single explanation. When we shine a beam across a room, we picture countless tiny photons flying straight. But if we try to trace their behavior more precisely, quantum mechanics tells a different story. A photon has no such definite flight path until something forces its possibilities to resolve into one history. It is not simply that we do not know the path. Rather, the universe itself has not chosen yet. All potential roots coexist in a shimmering mathematical form we call the wave function. The wave function is not a soft cloud of energy or a whispering ghost drifting through the air. It is a calculation, an evolving rule that predicts likelihood. Yet this calculation behaves as if it were real enough to bend and overlap with itself. When two paths are available, the wave function spreads through both. Where the overlapping waves are in sync, the chance of detection rises. Where they cancel, the photon avoids. The pattern on the wall in the double opening experiment is not a message from a classical wave. It is written by probability itself showing its structure. What makes this so unsettling is that the photon does not split into two smaller photons. It remains one indivisible quantum of light. We do not detect half photons. And yet, before we observe it, the mathematics insists the photon has no single location. This is not just a small detail. It denies the very idea of a path. We are so used to imagining everything tracing a route through time that we forget this idea came from everyday experience. The photon does not care what feels familiar to us. It follows the laws of quantum behavior, and those laws do not include a requirement for a single trajectory. Some scientists have tried to tame the strangeness by saying the wave function only represents what we know, not what is. But this explanation struggles when the wave function predicts striking interference outcomes that would be impossible if the photon did secretly choose one path early on. The interference pattern proves the photon does not have a hidden definite path. The possibilities must exist together in a single quantum state. Then, at the moment of interaction with a detector or screen, most of those possibilities vanish. Collapse arrives like a verdict. We observe collapse every day in the most ordinary acts: turning on a light switch, reading a screen, looking at a star. The photons reach our eyes and each one manifests at a precise point. In that moment, the spread of probabilities shrinks to a single outcome. Yet nothing in the core principle of quantum theory instructs this to occur. The equations predict smooth and reversible evolution. Collapse is sudden and irreversible. Where does it come from? Why does the universe make certainty appear only at certain moments? Some experiments have pushed collapse to its limits. Researchers have observed interference with ever larger and more complicated particles. Clumps of atoms containing hundreds or thousands of constituents still behave like waves if isolated well enough. The boundary where collapse becomes unavoidable is not determined by size alone. It depends on how strongly the system is connected to the rest of the universe. Even a single photon loses its quantum grace if it scatters from a stray air molecule. Interaction destroys isolation and probability becomes fact. This leads to a popular concept called decoherence. It says collapse is not a special feature of nature, but a practical result of complicated interactions. The environment becomes entangled with the system and steals away the fragile interference effects. To maintain a state of superposition is to maintain perfect silence between the system and everything else. But the universe is loud. Noise creeps in from every direction and reduces the wave function to the behavior of classical matter. According to this view, collapse is not a rule. It is an illusion created by lost information. Yet even decoherence cannot fully answer the deeper question: why does one outcome appear instead of another? Why do we see a specific dot on the screen instead of the cloud of maybes? When the wave function interacts with the world, countless branches of possibility become connected to different histories. Decoherence says those histories no longer interfere, but it does not explain why we only experience one of them. The switch from maybe to truth remains unsolved. This is the heart of what physicists call the measurement problem. The rules work perfectly to predict probabilities. The rules fail to tell us what event selects the final result. That choice is at the center of every observation in physics. It is at the center of every moment in our lives. Yet we do not know what causes it. Perhaps there is a hidden layer of physical law. Perhaps we have accepted an incomplete story. Light becomes the perfect subject for this mystery because it dances on the edge between the known and the unknown. It can be guided by mirrors with perfect obedience. It can be counted one photon at a time with astonishing precision. But it can also act like pure probability, drifting without destination. The dual nature of light is not two separate natures. It is one nature that we do not yet fully comprehend. When a photon travels across the ocean of space, it carries energy and momentum. According to Einstein, that means it also influences gravity. Even without rest mass, the energy of light curves space-time. A photon changes the geometry of reality just by existing. This is a clue. If possibilities of different photon paths imply tiny differences in space-time curvature, then a superposition of paths might also be a superposition of tiny gravitational fields. Could the fabric of space-time itself refuse to support multiple realities at once? Some of the greatest scientists of our time have taken this idea very seriously. They propose that gravity might be the silent enforcer that pushes quantum possibilities to become classical facts. In this vision, collapse is not a mistake or an approximation. It is a consequence of the geometry of the universe. Light does not collapse because it is measured. It collapses because space-time cannot be in two shapes at the same time. The photon must choose a path because the cosmos demands a single curvature. If that is true, then the boundary between the quantum and classical worlds does not depend on human devices or environmental noise. It would be written in the strength of gravity and the distribution of energy. The closer physics gets to understanding that boundary, the closer we come to a new theory that unites the realm of particles with the structure of galaxies. Every time a photon lands on a wall or enters a detector, it might be telling us a story about how space-time forces decisions. Perhaps the universe itself is performing a measurement. Perhaps collapse is the moment geometry becomes definite. Yet this is only a hypothesis. The evidence is still being gathered, and until that evidence becomes clear, the photon remains an ambassador from a world where many futures coexist until one becomes real. Light challenges our intuition because it does not behave like anything we evolved to understand. Our ancestors learned to track stones, spears, and prey. Objects had positions and momentum and followed clear paths. But photons do not belong to that world. They are excitations of a quantum field that pervades the universe. They are not small balls. They are not tiny waves in the air. They are disturbances in the very structure that defines what light is. When we detect them, they appear as particles because the field interacts in discrete chunks. When we let them go free, they evolve according to the mathematics of superposition. They are not switching forms. They are revealing different sides of the same underlying reality. The strangeness grows when we consider that a photon does not experience time the way we do. Traveling at the speed of light means experiencing no passage of time at all. From the photon perspective, emission and absorption are the same event. There is no in-between, no corridor of possibility slowly unfolding. Yet our measurements show interference patterns that depend on the exact geometry over long distances. How can light interact with all available possibilities if there is no time for it to explore them? The mathematics answers simply by stating that the wave function contains all paths at once. But the philosophical discomfort remains. We are forced to accept that reality can operate in ways far outside our common experience. This is why the collapse question is not a small technical detail. It asks when and how the universe decides which description becomes the one we observe. If collapse is physical, we need a mechanism. If collapse is only in our knowledge, we must accept that all outcomes exist in some structure we cannot directly perceive. The universe has a truth, but quantum mechanics only gives us probabilities for what that truth might be until the moment it is revealed. In the earliest days of quantum theory, some believed the puzzle would resolve itself with better understanding. After all, this was a brand new field. Perhaps collapse would make sense once we learned more. But decades passed. Experiments became more precise. The double opening pattern was reproduced with electrons, atoms, even large molecules containing many dozens of atoms. The wave nature persisted far beyond what anyone expected. The collapse point did not move predictably with size or mass. Instead, it seemed to move whenever the system interacted with its surroundings. The more isolated the system, the more quantum it remained. This convinced many that collapse is not an internal property of particles, but a failure to maintain purity when the environment becomes involved. The world is constantly filled with stray photons, vibrating molecules, and gravitational influences from every direction. Any tiny nudge can scramble the delicate alignment needed for interference. In pure isolation, superpositions live. In contact with the universe, they dissolve. But this interpretation creates a troubling split. If quantum behavior is the most fundamental and collapse is only an illusion caused by lost information, then reality is truly composed of vast networks of entangled possibilities. Everything exists in superposition all the time, with decoherence hiding that truth from our limited observations. We experience a simplified reality, not because the universe is simple, but because our senses and instruments are blind to the complexity. However, there remains one issue that decoherence alone cannot settle. It can explain why interference disappears. It cannot explain why one outcome becomes the one we witness instead of another. The patterns of probability become real events. Yet the theory offers no rule for why any specific event is chosen. Something must break the symmetry of possibility. One idea suggests that consciousness causes collapse. Observers turn potential into reality. This idea has been popular in public imagination, but it holds no solid scientific foundation. Collapse happens in detectors with no human present. It happens in distant galaxies, long before life existed. The cosmos does not wait for minds to measure it. Consciousness is a late arrival, not a fundamental component of physics. Another idea says collapse is simply an update of our information, and that multiple outcomes continue to exist somewhere in a grand multiverse. This interpretation avoids adding new physical rules, but it multiplies the scale of existence beyond comprehension. It also removes collapse as a physical event, making it a feature of description rather than reality. Then there is a more grounded possibility. Maybe collapse is driven by something that is universally present, universally influential, and fundamentally connected to existence itself. That something could be gravity. Gravity is woven into the geometry of space. It affects everything with energy. Even a photon with no rest mass carries energy and momentum. Therefore, it influences gravity and is influenced by gravity. If a photon path splits into multiple alternatives, each alternative carries energy in a slightly different location. That means each alternative creates its own version of space-time curvature. For a moment, the universe might contain several possible shapes at once. This idea leads to a radical proposal. Perhaps space-time geometry cannot support multiple conflicting shapes. The universe may demand that only one curvature can persist. If a quantum system creates superposed geometries, gravity steps in and enforces a single one. Collapse would then be a natural consequence of physics. It would not depend on observers or environments. It would depend on mass energy and the structure of space-time. Even light would be subject to this enforcement. Its potential paths would collapse into one when the gravitational difference between them becomes significant. This idea, proposed by thinkers such as Roger Penrose, invites a new way of looking at the photon. It becomes a traveler not only through the landscape of probability, but through the contours of space-time. Each potential route is tied to a slightly different universe. Collapse may be the moment when the photon and the universe agree on which shape reality will take. The key question is how to test this. Gravity is an incredibly weak force compared to electromagnetism. The gravitational influence of a single photon is unimaginably tiny. Yet the universe has vast distances and long timescales. Perhaps in space, where photons can travel for billions of years, gravitational effects accumulate. Perhaps the stars themselves are laboratories where gravity quietly performs collapse on cosmic scales. Light behaves like a wave of probability until space-time forces its hand. If this is true, collapse becomes a dialogue between quantum rules and cosmic structure. The simplest particle we know becomes a messenger of the deepest questions. Understanding the moment of collapse may reveal not only what light is, but how reality is chosen. Even at this early stage in our exploration, one thing is clear. Light does not simply travel. It negotiates with existence, and every photon we observe has survived that negotiation and arrived with a message. Possibility once existed, but now truth stands in its place. Gravity feels ordinary because we live under its rule every moment. It keeps our feet on the ground. It shapes the sway of oceans and the arc of falling apples. It guides planets around the sun and gathers stars into swirling galaxies. It has been working tirelessly since the first flicker of time, yet it hides behind its own familiarity. We rarely stop to ask how a force so gentle in our daily lives could also be the great architect of the cosmos. We accept gravity as a constant presence without questioning what it really is. For most of human history, gravity was simply a pull between things with mass. Heavy objects tugged on each other. Earth pulled the moon, and the moon pulled the tides. Isaac Newton described this attraction with astonishing accuracy using mathematics that changed the world. But he did not explain why gravity exists. Newton himself admitted this, writing that the idea of masses reaching across empty space to pull each other with no contact at all was a mystery beyond imagination. His theory told us what gravity does, not what gravity is. Centuries later, a quiet patent clerk named Albert Einstein saw a deeper truth. He proposed that gravity is not a force at all. It is the shape of space-time. Mass and energy distort the geometry of the universe, and this curvature guides the motion of everything within it. Planets follow the straightest possible paths through a space that is itself bent around the sun. The apple falls toward the ground, not because Earth grabs it, but because Earth has shaped the surrounding space-time so that downward is simply the natural direction to move. Einstein united space and time into a single fabric. What happens in one affects the other. Clocks tick more slowly near strong gravitational fields. Distances stretch and compress depending on how space-time is warped. Light, which has no rest mass, still obeys this curvature. A photon travels straight, but straight and curved space-time can lead around stars or through the depths of a gravitational well. This view turned the universe into a dynamic stage where geometry and motion are inseparable. General relativity, the theory Einstein built, has passed every test thrown at it for more than a century. It explains the orbits of planets with unmatched precision. It predicts the bending of starlight near massive bodies, a prediction confirmed during a famous eclipse when astronomers saw the positions of stars shift around the sun. It describes the crushing gravity inside black holes where not even light can escape. It predicts gravitational waves, ripples of space-time created by titanic accelerations of mass. Those waves have been observed from colliding black holes and shining neutron stars many millions of light years away. General relativity has earned its throne as one of the most successful theories in science. Yet there is a complication. Quantum mechanics rules the world of the very small. General relativity rules the world of the very massive. Both are tested. Both are true in their realms. But when we try to combine them into a single picture, the mathematics breaks. The quantum laws that describe particles operate with uncertainty and probability, while general relativity describes smooth deterministic geometry. One theory says nature is grainy and governed by chance. The other says space-time is continuous and governed by curvature. They speak different languages, and so far no translator has fully reconciled them. Gravity stands apart from the other forces in another way. The electromagnetic force, the strong nuclear force, and the weak nuclear force all have quantum descriptions. They are carried by particles that can be created, destroyed, and entangled. Gravity, in contrast, has no confirmed quantum particle. Some theories propose that a particle called a graviton should exist. If so, gravity would also behave as a quantum interaction. But no graviton has been detected, even in the most sensitive experiments. The gravitational effects of single particles of light or matter are so incredibly small that measuring them directly remains one of the greatest challenges in physics. Despite this difficulty, quantum mechanics insists that energy and mass are equivalent. A photon contains energy, and energy must influence gravity. That means even the smallest quantum events ripple through the geometry of space-time. But how? If a particle exists in multiple possible locations at once, does space-time take on multiple shapes at once? If so, what happens to those shapes when only one outcome becomes real? General relativity is silent about probabilities. It describes definite curvature created by definite mass. It does not know how to curve in a configuration that is only perhaps true. We stand at a crossroads. On one path lies the smooth geometry of Einstein. On the other lies the unpredictable quantum behavior of particles like photons. The fact that both succeed so spectacularly suggests they are glimpses of a deeper underlying truth. But until that truth is uncovered, the boundary where waves of possibility meet the solid structure of space-time remains a profound mystery. Gravity is not just a force that shapes stars. It might also shape the very act of measurement itself. It could be the key to understanding why quantum possibilities collapse into single outcomes. It is quiet and steady, yet its influence reaches everywhere, including the unseen realm of particles. It is always present, always watching from behind the curtain of the familiar. As we listen more closely to this background actor of the universe, we may discover it is not a background player at all. It might be the director of every scene reality allows to unfold. Gravity does not announce itself with sudden flashes or bursts of power. It works with patience carved into the bones of space-time. Even when unbelievable masses collide and send out gravitational waves, the signal that reaches us is so faint that it requires detectors of unimaginable sensitivity to notice. The universe whispers through gravity. Yet those whispers hold together galaxies larger than anything our minds can comfortably picture. The quiet nature of gravity is not weakness. It is the steady hand that arranges the cosmos. If we could remove gravity from existence for even a moment, planets would drift off course and solar systems would unravel. Stars would tear apart into scattering clouds of hydrogen. Galaxies would dissolve into lone wanderers, crossing a cold and endless void. Matter would lose the sculptor that shapes its destiny. Without gravity, the universe would be a chaotic spray of particles with no structures to give them meaning. Everything we see, from the spiral arms of our home galaxy to the delicate dance of a leaf falling through air, owes its behavior to the curvature of space-time. Einstein taught us that space-time is not a passive stage. It is an active participant in the story of existence. When mass or energy appears, space-time bends. When mass or energy moves, the curvature changes. The laws of motion we learn as children become a deeper truth. Objects travel freely unless something interferes. But in general relativity, the interference is often the shape of the universe itself. A planet orbiting a star is not being pulled. It is following the most natural path in a warped geometry. If we could somehow straighten space-time, the planet would fly off in a straight line. It is the bending that keeps it close. This geometric view creates a challenge when we look toward the quantum world. Quantum mechanics claims that particles do not have definite positions until measured. They occupy superpositions, combinations of possibilities that evolve smoothly and mathematically. But according to general relativity, the curvature of space-time depends on where energy and mass are located. If a particle does not have a single location, then what shape does space-time take? The question sounds like a puzzle, but it is really a warning that our theories are incomplete. Physicists have tried to build bridges between these two realms. One attempt imagines quantizing gravity so that space-time itself comes in discrete levels, like energy levels in an atom. In such a theory, space-time could become entangled with particles, and collapse would be just another quantum process. But no experiment yet confirms this view. Another approach, called loop quantum gravity, suggests that space-time might be woven from tiny loops and knots on scales far too small for current instruments to see. In that picture, curvature arises from how those loops twist together. Yet many predictions remain beyond our reach. Other bold attempts attempt to merge quantum physics with the geometry of black holes and horizons. Ideas like ADS-CFT propose that space-time could emerge from a deeper quantum information structure. If so, gravity might be a shadow cast by the interactions of particles and fields that live on a kind of boundary of the universe. Space and time would not be fundamental. They would be consequences. This would be a thrilling revelation, but the mathematics is complex and the experiments required to test it remain a distant hope. While the largest dreams of theoretical physics continue to unfold, the stubborn facts remain. We have two brilliant frameworks that refuse to cooperate. Each claims dominion over a different scale. Quantum mechanics governs the smallest particles. General relativity governs stars, galaxies, and the expanding universe. But what happens in the places where both should apply at once? What happens at the border? The heart of a black hole is one such region. Matter collapses to unimaginable density, and quantum effects cannot be ignored. But general relativity predicts a singularity where time ends and the known laws break entirely. Something must replace that prediction, but we do not yet know what. The earliest moments after the universe began are another region where quantum fields and extreme gravity collide. Yet our theories blur in that storm, and we are left with limited clues. Even a single photon traveling near a massive star asks the universe to reconcile these domains. The photon is a quantum object described by a wave function that spreads across many possible positions. But the star shapes space-time in a definite way. It cannot bend geometry by degrees of maybe. It must curve around real energy in real positions. Somehow the photon must obey both sets of laws. Somehow quantum uncertainty must coexist with gravitational certainty. This tension invites an intriguing perspective. Perhaps gravity has always been the missing ingredient in the story of collapse. Perhaps collapse is the moment when quantum possibilities become too costly to maintain in the structure of space-time. A photon can explore multiple routes while the gravitational differences are small. But when those differences grow, when the universe must bend in ways that conflict, gravity may eliminate the extra possibilities. If true, This means collapse is not a problem. It is a resolution. It is the universe choosing a consistent shape over inconsistent ones. Light remains free and uncertain only while the geometry allows it. Then gravity steps in and says, choose. This is not merely speculation. It is a testable idea. Scientists around the world are designing experiments to push photons into delicate quantum states while exposing them to gravitational differences. They seek the point where interference fades, not because of environmental noise, but because space-time itself cannot support a superposition any longer. If observations confirm this, collapse will gain a physical cause grounded in the shape of the universe. Gravity would no longer be just a background actor. It would be the adjudicator of reality, deciding which possibilities can survive. It would become as important in the smallest corners of existence as it is in the largest. But for now, gravity remains a mystery wearing familiarity as its disguise. We feel it pull, but we do not truly understand why space-time curves or how that curvature relates to the quantum fabric beneath. Every falling apple is a reminder that we have uncovered only a fraction of the truth. Light will help us look deeper. The way a photon travels, interferes, and collapses may reveal how gravity works in the quantum domain. And when we unlock that relationship, we will step closer to a theory that describes all of reality at once. Gravity feels like the universe's simplest rule, yet every attempt to understand it more deeply leads us into a maze of unanswered questions. We know how to calculate its strength between planets. We know how it shapes the orbits of stars near supermassive giants that lurk at the centers of galaxies. We know that time itself slows as gravity grows stronger, but we do not know what gravity is made of. We do not know whether it is a smooth bending of space-time or the collective effect of countless unseen quantum interactions. We do not know why it is so immeasurably weaker than the other forces that govern the microscopic realm. Consider a tiny magnet. It can lift a paperclip against the gravitational pull of the entire Earth. Electromagnetism rules the small world with ease, while gravity barely whispers. Yet in the grandest arenas of the cosmos, gravity becomes the ultimate authority. Stars burn for billions of years because gravity compresses fuel to ignite nuclear reactions. Galaxies spiral because gravity binds their countless suns into vast structures. The universe itself expands and evolves under gravity's guidance. How can a force so weak become the master of the heavens? Some scientists wonder whether gravity's weakness is a sign that it is not a fundamental interaction at all. Perhaps it is an emergent property, the large-scale result of something deeper happening on the smallest scales. Just as temperature emerges from the collective motion of countless molecules, gravity might emerge from quantum information that organizes space-time into something that feels continuous. If so, we have been studying the shadow rather than the substance. This puzzle lies at the heart of why quantum mechanics and general relativity resist unification. Quantum theory demands discreteness. Energy exists in exact amounts. Interactions are recorded in quanta. Information is conserved through delicate correlations called entanglement. General relativity demands continuity. Space-time can bend by any amount needed. Events flow smoothly. The two views agree on countless experiments, but refuse to describe a shared reality. Photons, children of the quantum world, move through gravity's curved geometry as if nothing was strange about the combination. Light follows the shapes space-time dictates, even while existing as a superposition of possibilities. That coexistence hides a contradiction. If the photon has no definite position, what exactly is space-time, curving around? If the photon explores many paths, is space-time curving in several ways simultaneously? If so, how does the universe resolve these conflicting shapes into the single geometry we observe? These questions gain importance when we examine the most precise experiments ever built. In laboratories around the world, physicists send particles through interferometers that stretch across long distances. They cool atoms to near absolute zero to reduce environmental noise. They shield delicate quantum states from unwanted disturbances. Their goal is to preserve superpositions for as long as possible. They want to see how far the quantum can travel before collapse arrives. Some experiments already reveal hints that gravity influences quantum coherence. When clocks are placed at different heights in Earth's gravitational field, their ticking falls out of sync by tiny but measurable amounts. The rate at which time flows depends on gravity's strength. For quantum systems that rely on precise timing, this difference can cause their phases to drift. Even photons, which do not experience time as we do, carry a phase that evolves relative to the geometry around them. If gravity alters that phase, superposition becomes fragile. If the drift grows large enough, the overlapping parts of the wave function can no longer maintain harmony. Interference fades. The photon begins to behave more like a particle with a definite path. This is not the same as collapse caused by measurement. It is a gentle erosion of quantum unity caused by gravity's subtle grip on time itself. We see a suggestion of this effect when light travels near massive objects. Gravitational lensing reveals that space-time bends the direction of light. But deeper inside the effect lies a question. If two possible routes around a star have slightly different lengths and time flows differently along each, how long can those possibilities coexist before gravity forces one outcome to win? On Earth, the differences are tiny. In the vastness of the cosmos, they may stretch across millions of years and unimaginable distances. A photon on a cosmic journey may begin in superposition, but gravity might steadily strip away its quantum freedom long before it reaches us. This perspective reframes our understanding of collapse. Instead of a sudden event triggered by measurement, collapse could be a gradual loss of coherence under the influence of spacetime. The boundary between quantum behavior and classical certainty would then depend on gravity's strength and the separation of possible paths. Tiny systems close together could remain quantum. Larger systems with more divergent gravitational impacts would collapse faster. This matches what we observe in the laboratory. Quantum behavior thrives in isolation and simplicity. Classical behavior emerges in complexity and mass. Yet there is still one crucial piece missing. Even if gravity destroys coherence, we still do not know what selects the final outcome. Decoherence explains why interference disappears. It does not explain why a single reality appears. Gravity might influence the timing of collapse, but does it decide which result becomes true? Some researchers believe the answer may lie in a new understanding of spacetime. They suggest that when quantum possibilities imply different geometries, only one can survive, because spacetime cannot be both flat and curved in different ways at the same moment. The universe must choose a single shape. Collapse becomes geometry selecting itself. Others argue that this idea may not hold. They suspect that spacetime can indeed exist in strange superpositions that we have not yet learned to measure. If so, gravity may not cause collapse at all. It may simply join the quantum dance, waiting for a more complete theory to reveal how the two worlds blend into one. What remains undeniable is that gravity touches every photon and every particle. Even the most delicate experiments cannot escape its reach. Gravity is always present, always there, always shaping the possibilities before we ever notice them. We live in a universe where certainty is precious and rare. Gravity might be one of the few forces that pushes the universe toward definite choices. It might be the quiet voice that says one path, not many. One outcome, not all. Light is the perfect witness to this quiet decision-making. A single photon carries the record of a journey where possibility gradually narrowed into truth. If we learn to read that record, gravity may finally reveal its quantum signature. Light feels weightless in every sense we usually understand. It does not pull objects the way heavy stones do. It does not drop to the floor. We cannot feel it pressing on our hands. A flashlight beam does not sag under its own burden. So when we say that light contributes to gravity, The idea seems to contradict our everyday experience. Yet physics tells us that mass is not the only source of gravity. Energy shapes space-time as well, and photons, though they have no rest mass, carry energy wherever they travel. A single photon can nudge space-time, however slightly, bending the universe around it. This truth emerges from the heart of Einstein's insight. Mass and energy are two ways of describing the same physical content. When energy increases, gravity strengthens. When mass decreases, energy must go somewhere. Light is pure energy in motion. It is the swiftest courier of influence allowed by nature. Because of this, the path of a photon is not a route through emptiness. It is a conversation with the geometry of reality. The photon moves along the straightest line space-time offers, but that line is shaped by everything else in the cosmos. The discovery that light is deflected by gravity was one of the earliest confirmations of general relativity. When starlight passes near the sun, the curvature of space-time guides the photon so that its direction shifts slightly. During a solar eclipse in the year 1919, astronomers traveled to isolated parts of the world to measure this effect. They saw stars appear in places slightly different from their usual positions. The universe had spoken in the language of bending light. Space-time was not a rigid backdrop. It was a living structure influenced by energy. Even photons play their part. If light is influenced by gravity, does it in return influence gravity? The equations suggest yes, though the effect is extremely small. It would take beams of unimaginable energy to curve space-time in ways we could observe easily. But at the quantum scale, perhaps the slightest curvature matters. A photon that exists in multiple possible paths would create multiple tiny distortions. The question then grows sharper. How long can the universe keep track of these distortions before deciding which one is real? Imagine a lone photon leaving the surface of a distant star. Its wave function spreads outward over unimaginable distances. Every possible path the photon might follow sits within that spreading cloud of possibilities. And yet each possible path carries energy in a different place. Space-time would need to curve around each potential location. For a moment, the photon drags multiple futures behind it. But those futures cannot all survive. The geometry of space-time must eventually settle into one consistent shape. This perspective pushes us toward a strange but powerful conclusion. The wave nature of light is a dance of possible energies, but gravity demands certainty. Even the smallest curvature is a claim on what is real. If possibilities differ in how they shape space-time, gravity may become impatient with uncertainty. The collapse of the photon wave function might not wait for a detector. It might occur whenever the difference between possible gravitational outcomes becomes too significant to ignore. This idea grows even more intriguing when we consider photons that carry high energy. The more energetic the photon, the more strongly it interacts with space-time. A gamma-ray burst exploding in a distant galaxy unleashes torrents of powerful photons. They race through the universe, threading their way around stars and through clusters of matter. If gravity shapes their fates and they shape gravity in return, then the collapse of their wave functions could be influenced by how violently they bend space-time. High energy means stronger curvature. Stronger curvature may mean faster collapse. Yet the universe often proves more subtle than our first guesses. There are regions where the gravitational influence of light becomes too important to ignore, but we cannot observe those regions directly. At the edge of a black hole, light spirals into darkness. It circles the abyss at speeds and energies beyond anything we can safely duplicate. In that extreme place, the difference between one possible photon path and another could make the difference between escape and capture. If gravity forces collapse, it may do so brutally and early near such monstrous curvature. There is another way to think about light and gravity. Photons carry momentum, and when they strike an object, they deliver a tiny push known as radiation pressure. This pressure is weak, but over time it can shape the tails of comets or the sails of futuristic spacecraft. If light can exert force in this manner, it is reasonable to imagine that it also exerts influence on space-time itself. The gentle push of a photon is a reminder that energy is never weightless in the deepest sense, even when it feels effortless. While the bending of starlight is now familiar, the idea that light itself contributes to gravity remains on the frontier of measurement. No human instrument has yet detected the curvature produced by a single photon. The effect is lost beneath the ocean of influences generated by planets, stars, and dark matter. But the mathematics remains firm. Where energy flows, space-time bends, and light is energy in motion. This leads us to a profound question. If light curves space-time and space-time curves light, is there a feedback loop that shapes quantum collapse? Every possible route a photon might choose has its own gravitational imprint. Perhaps collapse is the moment when the photon must stop trying to sculpt multiple future geometries and commit to one. Reality cannot split endlessly. Geometry demands a decision. Physicists have begun to explore this possibility with increasing interest. They ask whether the gravitational influence of superposed particles could be measured. They ask whether gravity might carry quantum information. If gravity has no quantum nature of its own, then it cannot support superpositions. It would force collapse of any quantum system that tries to place energy in more than one gravitational configuration. In this view, collapse is not a mysterious rule. It is a consequence of the incompatibility between uncertain energy and definite curvature. The more we study light, the more it reveals that it is not merely a wave or a particle. It is a messenger between realms that refuse to share a common description. Light belongs to quantum mechanics, yet answers to general relativity. It is a bridge suspended between chance and geometry. As we continue to follow that bridge, we approach a theory that might unite the smallest and the largest. The bending of a single photon path by gravity becomes a clue carved into the cosmos. Perhaps in the language of curvature and collapse, the universe is telling us where certainty is born. When we look closely at light behaving under gravity, we discover that every photon carries a story about space-time. The photon has no rest mass, yet general relativity does not care. It sees energy as a source of curvature, and a photon is pure energy bound to motion. So as a photon moves, it does not glide through a neutral void. It leaves a trace in the geometry behind it, a faint imprint of where energy once traveled. Even if that imprint is far too small for our instruments to notice, nature notices. Space-time reacts to every influence, no matter how delicate. Consider a single beam of sunlight striking a metal surface. The light warms the metal and gives its atoms a small push. This push is the action of radiation pressure. Over long periods, the sun's light can erode dust from an asteroid surface, or steer the delicate solar sails imagined for interstellar travel. The push of light proves that photons transfer momentum. That momentum must travel through space-time carrying gravitational influence. Though the bending they cause is tiny, the principle is absolute. Nothing with energy can avoid contributing to curvature. This idea shows that photons are not merely passengers guided by cosmic geometry. They are also participants. Their existence shapes the universe, just as the universe shapes them. Every quantum of light is a sculptor, and the sculpture is the map of reality. Now imagine two possible paths for a single photon. In one possibility, the photon passes slightly closer to a massive star. In the other possibility, it passes slightly farther away. In both possibilities, the photon influences the curvature differently. The closer path demands a small but specific bend in the local space-time structure. The farther path demands a slightly different shape. The photon wave function would then imply two distinct geometries. It is as if the universe must prepare two versions of itself, each tailored to a different possible journey. But the universe we experience never splits into separate geometries. It always settles into one shared shape. So something must decide which version persists. If quantum superposition attempts to impose conflicting bends in space-time, gravity may be the authority that refuses the contradiction. Collapse could be the moment the universe commits to one particular curvature, erasing all others. Some thinkers argue that this decision might only occur when the gravitational differences grow large enough to be felt by space-time. Tiny discrepancies in curvature may be easily tolerated, letting a photon explore many paths at once. But with greater separation, a tipping point could arrive. Past that threshold, the wave function cannot maintain unity. Collapse becomes inevitable. This would mean that the transition from quantum ambiguity to classical certainty is not random. It is guided by the geometry of existence. Now extend this picture beyond a single photon. Consider beams of light bouncing many times between mirrors in an interferometer. Each bounce increases the potential for gravitational effects because the photon has more chances to leave tiny distortions behind. On short scales, gravity is too weak to matter. But as the scale grows, the wave function has more room to spread. Its gravitational effects may become easier to distinguish. In principle, we might design an experiment where superposed photon paths create differences in the curvature that are just large enough for collapse to occur. Scientists attempt such feats using precise timing and long distances. They hope that gravity will reveal its influence in ways decoherence alone cannot explain. Even the cosmos itself might conduct these experiments for us. Light that travels across billions of years encounters variable gravitational landscapes. It weaves between galaxies, runs near clusters, skims past black holes. Each encounter may test the stability of superposition. If gravity drives collapse, the universe becomes a grand interferometer. The results reach us as photons that no longer show signs of their quantum origins. Collapse would have happened long before they hit our telescopes. A question emerges. If gravity can cause collapse early, why do we still see interference patterns from starlight or in controlled experiments on Earth? The answer may lie in the scale of the gravitational difference. When paths are extremely close together, the universe sees almost no difference in curvature and superposition remains intact. The wave function stretches like a flexible membrane that does not tear as long as the tension between possibilities stays small. Collapse waits in patience until geometry demands a choice. We must also consider that light can be entangled. Two photons produced together can share a single quantum state, such that measuring one affects the behavior of the other, no matter how far apart they travel. Entanglement defies locality, but remains within the rules of quantum information. If gravity collapses each photon independently based on its own influence on space-time, would entanglement survive? The question cuts to the core of the mystery. If collapse is tied to geometry, then entangled photons separated by meaningful curvature might lose their shared identity. The connection between them would fray under gravity's quiet insistence on local reality. Yet experiments show that entanglement remains robust over large distances. Photons sent to orbiting stations still exhibit quantum correlations with their twins on Earth. This suggests that gravity does not easily sever entanglement. It might imply that space-time can support subtle superpositions after all. Or it may simply mean that the gravitational differences involved so far are too small to force collapse. The truth remains hidden behind the limits of our measurements. Light, therefore, sits at an intersection where theory becomes conflict. Quantum mechanics demands superposition. General relativity demands definite curvature. Both cannot always be right in the same form. That tension hints at something deeper, something waiting to be discovered in places where possibilities bend the universe in different ways. Light carries energy. It carries information. Perhaps it also carries the seed of a gravitational rule that enforces what is real. When we shine a beam or observe a distant galaxy, we are witnessing photons that have navigated this tension. Their collapse into definite outcomes may mark the moment when gravity and quantum law come to agreement. Light does not simply reveal our universe. It reveals the rules that guide the birth of certainty. Light travels with a confidence that seems effortless. It crosses the vast gulf between stars without slowing or forgetting its direction. It threads its way through the curved geometry sculpted by planets and black holes. Yet beneath that elegance lies a delicate balancing act. The photon must navigate a world where two competing descriptions of reality hold authority. Quantum mechanics allows it to exist everywhere its wave function extends. General relativity demands that energy occupy definite places so that curvature can respond. To keep moving at all, the photon must constantly negotiate between possibility and certainty. The strange coexistence of these principles becomes clearer when we think about momentum. A photon always carries momentum, even though it has no rest mass. That means it can push objects. It can create tiny forces that accumulate over time. In the deep vacuum of space, sunlight can steer a spacecraft equipped with reflective sails. The momentum of millions of photons adds together to form a gentle but persistent wind. If we accept that momentum is a measure of motion wrapped in energy, then we must also accept that momentum contributes to gravity. Light may feel weightless, but it cannot escape the accounting that governs space-time. Picture a photon rising from the surface of a star. As it climbs away from the strong curvature near the stellar core, it loses energy to gravity. Its color shifts slightly toward the red end of the spectrum. This gravitational redshift has been measured on Earth using photons traveling only a short distance upward. Even over that small height, the effect is real. Light responds to gravity not only in its path but in its internal energy balance. The photon carries gravity's signature with it. If energy shapes space-time, then the very existence of that photon forces the universe to acknowledge where it might be found. But if it exists in many possible places at once, the universe faces conflicting demands. General relativity cannot allow space-time to curve in several different ways simultaneously, at least not in the world we see. That is why some physicists suspect that collapse occurs when those possible curvatures begin to differ in meaningful ways. The wave function may try to stretch into many futures, but gravity may limit how far it can stretch before it must resolve into one. This concept gains sharp teeth when we consider what would happen if light carried much more energy. Imagine a photon packed with so much energy that it significantly alters the curvature around it. The wave function spreading of such a photon would create a family of potential universes, each with different distortions. The larger the differences between those distortions, the faster gravity might act to settle the outcome. In this sense, collapse could scale with energy. More powerful light might choose a definite path sooner. The universe may tolerate ambiguity only while the consequences remain negligible. The universe has natural engines that can generate such powerful photons. In the hearts of galaxies, supermassive black holes twist magnetic fields into colossal jets that spit out particles and radiation. Gamma-ray bursts erupt when massive stars collapse or when neutron stars collide. These events produce photons millions or even billions of times more energetic than the ones coming from a cozy desk lamp. The collapse of their wave functions might reveal subtle hints of gravitational influence. If we could observe interference patterns in such extreme light, we might discover the limits of quantum behavior in a warped space-time. Another aspect deepens the intrigue. Although photons have no rest mass, they possess spin, a quantum property linked to angular momentum. Spin interacts with curvature in ways that still challenge full understanding. If the wave function includes multiple possible directions of spin or multiple trajectories that twist differently through gravity, collapse might again become a negotiation between geometric consistency and quantum possibility. Whenever curvature has to choose a shape, the photon may be pushed into a single fate. There is also a thermodynamic angle to ponder. In the universe, entropy tends to increase over time. Processes unfold in the direction that spreads information wider and mixes states together. Quantum collapse appears to move in the opposite direction. It selects one state and erases the rest. But if collapse results from gravity forcing a single space-time geometry, then it is not erasing information. It is preserving the only geometry consistent with the laws of relativity. The information that disappears from the wave function might live on silently in the shape of the universe. We must also address what happens when vast numbers of photons share space. In a star or a furnace, photons constantly interact with matter and each other. Their combined energy curves space-time more intensely. Their paths are influenced not only by massive atoms but by the ocean of radiation itself. In such a place, collapse might be inevitable and rapid. Light becomes localized quickly because the number of possibilities creates too much gravitational conflict. That may be why classical behavior dominates on large scales. The universe has too much energy spread in too many ways for quantum ambiguity to endure. The boundary between quantum and classical is therefore not a sharp line drawn at some fixed size. It is a shifting frontier determined by how gravitationally sensitive the possible configurations are. A single isolated photon can remain in superposition for a long time if its paths produce negligible differences in curvature. But as soon as those differences grow, collapse lurks close by. This places gravity alongside decoherence as a candidate for explaining how everyday certainty emerges from quantum strangeness. These ideas raise one more profound question. If a photon influences gravity while in superposition, does space-time itself enter a superposition? If gravity enforces collapse, this cannot last long. But if future experiments reveal that superposed gravitational fields exist even briefly, gravity itself may be quantum after all. That would transform our search entirely. Collapse would no longer be gravity imposing classical behavior. It would instead be a clue pointing toward a deeper, unified quantum gravity. The photon would still be the messenger, but the message would change. The universe might whisper that space-time is not yet understood. The answer could determine the fate of physics. If gravity causes collapse, we gain a new rule that binds probability to geometry. If gravity does not cause collapse, then space-time can live in uncertainty, just like anything else. Either outcome leads to breathtaking consequences. The path forward demands experiments that push light into states where gravity can no longer hide behind its usual subtlety. We stand on the edge of a realization. Light is not merely something that passes through the universe. It participates in shaping reality. Its wave function is not only a map of possibility, it is a negotiation with the curvature of existence. When we finally understand how that negotiation is settled, we will understand more deeply how the universe decides what is true. Roger Penrose has spent a lifetime tracing the edges of reason where mathematics and reality intertwine. He does not shy away from the deepest mysteries. Instead, he walks toward them with calm curiosity. In his view, the contradiction between quantum mechanics and general relativity is not a mere inconvenience. It is a clue that we are missing a fundamental rule of nature. Penrose believes that gravity, the shaper of space-time, may also be the ruler that forces quantum possibilities to collapse into definite outcomes. To understand his idea, we must step into the realm where geometry becomes fragile. Quantum mechanics tells us that a particle can exist in a superposition of different places. General relativity tells us that mass and energy curve space-time. Combine the two statements and something startling appears. A particle in superposition creates multiple versions of space-time, each with slightly different curvature. The universe would need to hold several geometries at once, stacked in probability rather than space. Penrose argues that such a situation is unstable. He compares these conflicting geometries to diverging branches of reality that cannot remain peacefully side by side. The universe must choose one. In his hypothesis, collapse is not triggered by measurement or observation, or even environmental disturbance. Collapse is driven by gravity itself. When the gravitational difference between the possible configurations grows large enough, the wave function can no longer sustain the superposition. The quantum state collapses into a single outcome. It is the geometry of the universe enforcing consistency. This proposal is known among physicists as objective collapse. It says, collapse is a real physical event, not merely an update to our knowledge. And unlike some other collapse theories that introduce mysterious rules disconnected from known physics, Penrose roots his idea in the familiar structure of space-time. According to him, gravity prevents absurd scenarios where mass exists here and not here at the same moment. It demands a single shape for the cosmos. Penrose even offers a rough way to estimate when collapse should occur. The greater the mass or energy separated in superposition, and the greater the distance between the alternatives, the faster collapse should happen. A tiny separation with tiny energy might last for a long time. A large separation with large energy might collapse almost instantly. This aligns with what we observe. Photons and electrons remain quantum easily. Large objects always behave classically. Yet the boundary is fuzzy because the relevant factor is not size alone. It is gravitational self-conflict. How much would space-time disagree with itself if all the possibilities remained alive? This view paints a picture of the universe as a decision-maker that prefers order over chaotic layering of incompatible shapes. Collapse becomes the moment gravity points and says this path is real. The others no longer shape the world. Penrose has long been fascinated by the internal harmony between mathematics and geometry. His work on black holes helped uncover that their formation leads to singularities, where general relativity loses predictive power. From those depths, he learned that gravity holds secrets beyond our current reach. If collapse is rooted in gravity, then quantum mechanics must eventually bow to the authority of space-time. The union of the two would not be a compromise. It would be the emergence of a deeper law. Not everyone agrees with Penrose. Some physicists argue that superposed space-time geometries might be perfectly acceptable in a future theory that successfully quantizes gravity. They say his concern arises only because general relativity is classical. Once space-time becomes quantum too, there may be no conflict. Collapse would not be required to preserve geometry. But Penrose responds that until such a complete theory exists, gravity remains the most likely cause of collapse. Instead of waiting for a new system to arrive, he looks for clues the current situation may already provide. Penrose also connects his idea to a more philosophical question. If collapse is objective and tied to the physical features of the universe, then consciousness does not cause collapse. Instead, consciousness becomes possible only because collapse yields a definite reality. Without definite outcomes, there would be no stable world for minds to form within. Awareness relies on certainty, and certainty may rely on gravity. These thoughts push deep into what it means for something to be real. If collapse is a fundamental process, then reality does not emerge from observation. Reality emerges from geometry. Quantum possibilities are allowed to drift only while gravitational tension is low. But eventually the universe demands a single truth. This enforcement creates the concrete world we experience. Our existence becomes a consequence of spacetime's insistence on consistency. Penrose's view also offers experimental predictions. If gravity triggers collapse, then under certain conditions, quantum interference should disappear faster than decoherence alone can explain. If researchers can create delicate superpositions of small masses or high-energy photons and alter the gravitational conditions slightly, they may detect a collapse rate that matches his formula. Penrose encourages such tests not because he is certain he is right, but because the question itself deserves clarity. The universe will reveal its rules only if we ask carefully and listen closely. The beauty of this hypothesis lies in its humility. It does not claim that we have already found the full answer. It says that gravity may be whispering a solution and we need better ears to hear it. Penrose believes that physics is on the brink of a discovery that will reshape our understanding of existence. Collapse may not be a mystery indefinitely. It might instead be the missing bridge between certainty and possibility. Light becomes a perfect subject for this investigation. A photon's energy curves space-time just enough to raise questions, but too little for easy measurement. It lives in the tension between quantum freedom and gravitational guidance. If gravity truly forces collapse, then each photon's journey is a battle between probability and geometry. and collapse becomes the moment gravity claims victory. The future of quantum gravity may begin with such tiny victories, each one recorded as a photon landing in a single place instead of many. The universe chooses, and that choice shapes the world. Penrose's idea forces us to rethink what it means for something to be undecided in the universe. In ordinary quantum mechanics, a particle can remain in a superposition indefinitely as long as nothing interacts with it. The wave function evolves smoothly, possibilities stay alive, and nothing collapses. But in the Penrose view, this is never entirely true. The very presence of energy ensures that gravity is involved from the start. Space-time monitors every possible configuration and waits for the moment when those configurations become incompatible. Collapse is not an interruption. It is the natural flow of reality reaching a point where indecision is no longer physically tolerable. This interpretation changes our understanding of measurement. Instead of the wave function collapsing because a detector interacts with the particle, the collapse occurs because the universe must keep its geometry consistent. A measurement device is simply a tool that magnifies this gravitational tension so we can observe the result. Collapse is not caused by looking. It is caused by the gravitational cost of leaving the universe undecided. Penrose draws inspiration from the structure of black holes to support this insight. A black hole creates a boundary called the event horizon, where information about what has fallen inside seems to disappear from the observable universe. But quantum mechanics resists this idea because information should never truly vanish. The debate over whether information escapes or is lost within black holes has fueled decades of research. Penrose sees in these arguments a sign that space-time and quantum law do not yet speak the same language. If gravity causes collapse, then information might not be lost. It could be transferred into the chosen reality that remains. The abandoned possibilities simply never become real enough to require preservation. The mathematics Penrose uses is not casual speculation. His collapse rule arises from the energy required to maintain different space-time geometries at once. When superposed states create more gravitational separation, they require more energy to coexist. The more energy required, the faster the collapse should occur. It is a countdown set by geometry itself. The universe does not allow debt to accumulate in curvature. When the bill grows too large, collapse pays it instantly. This has a striking implication. Collapse is not random in the purest sense. The final outcome might involve chance, but the timing of collapse follows a physical rule. In many interpretations, collapse is a mysterious event added to quantum mechanics to match what we see. In Penrose's interpretation, collapse is a real physical phase change. It is as fundamental as a block of ice turning into liquid water when temperature rises. There is a threshold after which one state of being must transform into another, but the physics community does not accept new ideas easily, and skepticism is healthy. Some physicists argue that Penrose underestimates the flexibility of general relativity. They suggest that space-time might be able to exist in a superposition without conflict, though we currently lack the mathematical tools to express it properly. If we eventually discover a fully quantum nature of space-time, then collapse might not be required at all. Instead of gravity demanding certainty, gravity might join the ambiguity. The wave function could include curvature as naturally as it includes position and momentum. This alternative path would point toward a future where superposed geometries are real features of nature. Collapse would return to being a concept tied to observation or environmental disturbance. But until experiments can measure tiny gravitational effects on quantum systems, the question remains unresolved. Penrose's idea is not easily dismissed because it is grounded in clear physical reasoning. Mass energy shapes space-time. Quantum mechanics allows mass energy to be uncertain. Something must give. The first serious attempts to test Penrose's collapse rule involve objects far larger than photons. Researchers try to place small mechanical resonators or micron-sized spheres into superposition, then observe whether they collapse faster than decoherence predicts. If they do, gravity is likely involved. If they do not, gravity may be innocent or too subtle to measure with current technology. These experiments require extraordinary isolation, chilling objects to temperatures near absolute zero and preventing any stray influence from shaking them into classical behavior. The challenge is enormous. Yet progress continues because the prize is nothing less than a new understanding of reality. Light offers a different path to testing the idea. Photons have no rest mass, but they still curve spacetime through their energy. If photons in superposition collapse earlier when their paths involve different gravitational potentials, that would be a powerful sign that collapse arises from curvature. Experiments on satellites already show that entangled photons maintain coherence through long journeys. This may mean that Earth's gravitational differences are too small to trigger collapse. But what about photons skimming the edge of a black hole or passing near a massive cluster of galaxies? The cosmos may hold answers we cannot yet measure. Penrose does not claim that his idea must be correct. He presents it as a possibility too compelling to ignore. He challenges the community to seek evidence rather than relying on tradition. His proposal honors both the elegance of quantum mechanics and the geometric power of general relativity by demanding that they interact. Collapse becomes a conversation between probability and curvature. It is a negotiation that always ends with a single truth. His hypothesis moves the boundary between the quantum and classical worlds into the structure of space-time itself. That would make gravity the guardian of consistency. The photon wave function remains spread out only while the gravitational consequences of its possibilities stay small. When the universe must warp too differently for each possibility, collapse arrives. The photon chooses, the geometry settles, reality proceeds. In this view, every act of collapse is a subtle victory of gravity over uncertainty. The universe simplifies itself continuously, refusing to balance too many futures at once. We experience that simplification as definite outcomes. A photon arrives here, not there. A star shines at one point in the sky, not many. The world feels solid because gravity edits the script. If Penrose's idea proves correct, collapse will no longer be a mystery. It will be the most ordinary event in the universe. A photon striking a screen will be just one more example of space-time resolving a conflict. Every measurement will be a story of gravity deciding the shape of the world. Penrose's approach ignites something that many physicists secretly crave: a return to physical meaning. For decades, the measurement problem has been handled with a mix of silence and practical convenience. The mathematics of quantum mechanics work so perfectly that many argue there is no problem to solve. They say the wave function is simply a tool, and collapse is nothing but an update to our knowledge. But Penrose refuses that escape. He asks a more honest question. What is the world actually doing when a superposition ends? If a photon interferes with itself and then suddenly stops doing so, that change is too real to ignore. In the realm of thought, Penrose imagines a tiny object held in two different locations at once. In each location, the object produces a slightly different gravitational field. These two gravitational states cannot coexist forever. There is a tension between the possible shapes of spacetime. As that tension increases, nature feels compelled to relieve it. Collapse solves the conflict. The object appears in only one place, and the geometry becomes single-valued again. The many unrealized futures fade, not because we looked away, but because they were never compatible with a single universe. This makes collapse something more elegant than a mysterious snap from chance. It becomes a physical reaction to a growing strain within the fabric of reality. A superposition is like stretching space-time in two directions at once. The more it stretches, the more collapse becomes inevitable. The universe acts to prevent a break in its structure. In Penrose's thought, collapse protects consistency. He does not stop at theory. Penrose collaborates with experimentalists who search for small but measurable signs of gravitationally induced collapse. They create delicate objects where the superposition would involve noticeable differences in mass distribution. Even a microscopic difference could matter if it is large enough to perturb spacetime. If the collapse happens more quickly than decoherence alone predicts, the experiment would point directly toward Penrose's rule. One group dreams of suspending a tiny mirror so small and so isolated that a single photon reflecting from it might create two possible mirror positions. Each position would slightly change the gravitational field. If that gravitational difference forces collapse, interference will vanish faster than expected. Another idea involves using beams of light that circle thousands of times between mirrors, amplifying the curvature they carry. A long enough path might push the gravitational differences across the critical threshold. If collapse happens sooner than environmental noise explains, gravity would be implicated. These tests are incredibly difficult. The slightest vibration from the world outside can destroy superposition before gravity ever gets a chance. Stray thermal energy, cosmic rays, or even a passing truck can ruin experiments that depend on silence at the level of individual quanta. Yet every year, researchers refine their techniques and push the boundary farther. The search continues because the reward is enormous. A demonstration that gravity causes collapse would redefine what quantum mechanics means. It would give physics a path forward that does not require infinite parallel realities or the avoidance of reality's hardest questions. Penrose also brings philosophy into the conversation, though always grounded in physics. If collapse is real and driven by gravity, then the emergence of definite reality is written into the structure of the universe. Consciousness does not select outcomes. Instead, consciousness becomes possible because outcomes are selected. A brain could never form stable thoughts if every neuron existed in superposition forever. The gravitational rule Penrose proposes would ensure that large collections of matter always collapse their possibilities quickly. Minds need certainty, and gravity may be the author of that certainty. This idea reshapes our place within the universe. We do not impose measurement on the cosmos. The cosmos imposes measurement upon itself. Light collapses not because we observe it, but because the geometry of the universe refuses to remain uncertain indefinitely. Every spark of illumination that reaches our eyes has passed through this cosmic judgment. Each photon has chosen one path out of many, so that reality may remain singular. There are critics who say, Penrose's reasoning relies too much on intuition. They argue that superposed geometries might be possible, and that collapse is still an illusion of decoherence. They claim that a fully quantum gravity theory would allow spacetime to adopt probabilistic forms, but these arguments remain hypothetical. Until a quantum gravity theory is proven, Penrose's view remains a compelling alternative grounded in the only gravitational theory we currently trust. General relativity demands definite curvature. Quantum mechanics demands indefinite position. Collapse could be where the two finally meet. Penrose does not deny that many open questions remain. How exactly does gravitational tension translate into collapse? What mathematical structure governs this process? Can the rule be derived from deeper principles, or must it be taken as fundamental? These are questions he invites the world to help answer. His view is not a finished solution. It is a direction. It is the suggestion that reality may enforce its own coherence through the shape of spacetime. Light once again becomes the perfect test. A photon carries energy. Energy shapes curvature. As a photon travels through superposition, each possible route is a hypothetical change in geometry. If collapse comes from gravity, then photons in strongly differing gravitational potentials should lose superposition earlier. By examining light near intense gravitational fields, or by crafting laboratory setups where photons encounter gravitational differences, we may catch collapse in the act. If the universe reveals that gravity governs collapse, we will step into a new era of physics where quantum mechanics and general relativity are no longer strangers. Collapse will be understood not as a problem, but as the mechanism that unites possibility with spacetime. Instead of forcing reality into separate theories for the small and the large, we will recognize that reality is one consistent fabric that resolves conflicts as they arise. Every photon that lands on a screen becomes a message from that fabric, telling us where the universe chose to bend its geometry. The true challenge is patience. Nature does not reveal its secrets until we find the right instruments and the right questions. But Penrose reminds us that the greatest discoveries begin with daring curiosity. If gravity enforces collapse, then the decision between what might happen and what does happen is not completed in the laboratory. It is written into the cosmos. Light carries that decision with it always. Each photon is a witness to the moment when possibility becomes truth. Physics often advances by stripping away illusions. Decoherence is one of the most powerful tools in that process. It takes the great mystery of collapse and explains at least a part of it through ordinary interactions with the universe. According to decoherence, superposition does not gently fade because the particle grows tired of uncertainty. It fades because the environment never allows perfect isolation. Every stray photon, every molecule vibrating in the air, every gravitational tug from distant stars represents an interaction that leaks information away. As that information escapes, the fragile quantum unity between possibilities begins to crumble. The wave function remains alive in principle, but interference disappears. We cannot tell the possibilities apart anymore in a way that produces quantum signatures. The world looks classical, even though deep down it may still be draped in overlapping maybes. Imagine a photon slipping through a long tunnel built to silence the outside world. The walls are chilled nearly to absolute zero so that no atoms tremble loud enough to disturb the photon's state. Even there, the photon cannot avoid the faint gravitational pull from Earth, the cosmic radiation from deep space, or the quantum fields that never truly sleep. Decoherence is not a villain. It is simply the sum of all interactions with everything else in existence. The universe is never truly empty. That crowding prevents the most delicate quantum effects from surviving long distances or large sizes. In this view, collapse is not a physical event. It is an illusion produced by lost coherence. We lose our ability to track the different branches of the wave function. They still exist. They still evolve. But once those branches become entangled with the environment, they no longer interfere. Each branch marches forward as if it were the only one. The others become unobservable and therefore irrelevant. Decoherence says, collapse is not real. The world only appears to choose because we can no longer see what remains invisible. This interpretation is elegant and powerful. It explains why small systems can behave quantum while big systems behave classical. A single photon, isolated well enough, can drift in superposition for long stretches. But a dust grain suspended in air collides with trillions of molecules every second. Its quantum possibilities collapse too quickly for interference to appear. A human brain composed of countless neurons interacting continuously with heat, chemistry, and light behaves as classical as a falling stone. Decoherence accounts for this with no new laws, only the recognition that entanglement spreads like spilled ink across a white page. Yet decoherence does not answer every question. It tells us why interference disappears, but not why one outcome becomes the one we experience. When a photon strikes a detector, many possibilities existed only moments before. Decoherence can hide those alternatives, but it cannot eliminate them. If all outcomes continue somewhere in the mathematics, why do we only witness one? Why is there a here instead of a cloud of everywhere? Decoherence removes the need for collapse in calculation, but not in experience. It shifts the puzzle without solving it. Still, decoherence gives collapse a kind of physical flavor. The environment becomes a measuring apparatus that never sleeps. Every interaction pulls information out of the wave function and imprints it into the world. A photon scattered from a molecule carries with it a hint of the photon's former possibilities. That information is now in the universe, inaccessible to us, but enough to prevent interference later on. Decoherence paints collapse as a practical phenomenon rather than a fundamental one. It says the world is constantly measuring itself, and that measurement leaves us with the illusion of definite outcomes. The biggest challenge arises when we extend decoherence to the scale of gravity. The environment is not only air molecules and stray photons, it is also space-time itself. Gravity reaches everywhere. It does not weaken to nothing at any distance. Even the faintest gravitational influence could carry information about where mass or energy may be located. If the wave function proposes two places at once, gravity may spread that distinction across the universe instantly. Decoherence could therefore be driven by gravity, not through collapse, but through universal entanglement. This realization narrows the gap between decoherence and Penrose's idea. Both suggest that gravity plays a role in deciding when the quantum becomes classical. The difference is subtle, but profound. Penrose says, gravity enforces a decision. Decoherence says, gravity leaks information that hides the quantum truth. One suggests collapse is real. The other suggests collapse is appearance. One calls collapse a physical law. The other calls collapse a matter of perspective. Light offers a special test case because photons can avoid many environmental interactions. A photon can travel through a vacuum for millions of years without scattering once. Decoherence has so little to work with in those conditions that interference can persist far beyond anything we can engineer in a laboratory. Yet the photon still carries energy, and gravity never lets energy go unnoticed. If decoherence is the only process at work, then even cosmic photons should retain superposition as long as they remain untouched. If gravity itself imposes a limit, then somewhere on that long journey, the photon must commit to one space-time geometry. That is why experiments with light in extreme gravitational environments are so important. They test the strength of decoherence against the possibility that gravity is more than a passive witness. Researchers send photons along paths separated in height so that they experience slightly different gravitational potentials. Even a difference of a few centimeters changes the flow of time ever so slightly. That change alters the phase of the photon wave function. If decoherence driven by gravity is powerful enough, interference will fade faster than we expect. The results so far hint that gravity affects quantum coherence, though not yet in a way that confirms collapse. Decoherence draws us into a deeper thought. Perhaps reality is always a grand quantum superposition, forever evolving without collapse. Perhaps definite outcomes arise only from our limited role as subsystems entangled with much larger surroundings. Reality would then be a vast structure of branching possibilities, all equally true. The world we see is the thread we occupy. Collapse becomes the narrowing of our own view, not a change in the universe itself. This interpretation is bold because it suggests that existence is richer than experience. Our perception of singular outcomes could be like walking through a forest at night with a flashlight. The beam reveals only one path, but the rest of the forest persists unseen. Decoherence dims the light on other paths until they cannot influence our future, but they never vanish. The other possibilities march on, unreachable yet real. And yet, if gravity eventually tears superpositions apart, there may not be many paths after all. The forest may narrow quickly as the shape of space-time forces decisions. The universe might not tolerate arbitrarily large branching. The truth could lie somewhere between these pictures. Decoherence may handle the practical part of collapse, hiding interference efficiently. Gravity may enforce the ultimate selection, ensuring the universe chooses a single geometry. If both ideas contribute, collapse is neither illusion nor sudden decree. It is a gradual negotiation across scales. Possibility fades step by step until nothing remains but fact. Light shows us that even the purest quantum traveler cannot escape this negotiation. A photon moves freely, carried by the wave function until the world demands certainty. Sometimes that demand comes from the environment. Sometimes it may come from gravity. Either way, decoherence ensures that the quantum veil never remains intact for long. The classical world is not separate from the quantum. It is built from it, sculpted by interactions that discipline freedom into form. There is beauty in this. The universe manages to be unpredictable without being chaotic. It balances freedom with responsibility. It allows possibilities to stretch as far as they can before calling them back into reality. Decoherence does not diminish the mystery. It illuminates the boundary where quantum wonder gives birth to everyday certainty. Light thrives along that boundary. Each photon carries the memory of a superposition that once gleamed with potential. Decoherence steals that memory piece by piece, leaving only the trace of one path. In that trace, we find the world we know. Time is not a universal drumbeat echoing equally everywhere. Einstein showed that gravity slows the rhythm of existence. A clock closer to Earth's surface ticks slightly slower than one a little higher up. This is not a trick of perception or gears. It is the fabric of space-time stretching time differently in different places. Every moment you live is shaped by where you are. You age a tiny bit more slowly while standing on the ground than someone in an airplane soaring above. Though the difference is small for humans, for the universe, it is a powerful rule that touches every particle and every photon. Quantum mechanics depends on time with exquisite sensitivity. A wave function evolves smoothly according to the passage of time. Every possible state it contains oscillates, rotates, or shifts with a rhythm set by energy. If two parts of a wave function experience time at different rates, they will drift out of step. Their phases will no longer align perfectly. When that happens, interference begins to weaken, even without any direct interaction with the environment. Gravity becomes a silent conductor, altering the tempo just enough to threaten quantum harmony. Scientists have measured this effect using the most precise clocks ever created. These clocks rely on the vibrations of atoms, which are quantum in nature. When two identical atomic clocks are placed at slightly different heights, the one higher up experiences weaker gravity and ticks faster. In the year 2010, researchers confirmed that even a height difference of less than a meter produces a measurable shift in time. The universe does not ignore small differences. It keeps strict accounts. This tiny rift in time becomes profound for quantum systems spread across space. Suppose a photon has two possible paths separated vertically. Along the lower path, gravity pulls harder, slowing time slightly more. Along the higher path, gravity relaxes its grip, letting time flow a little faster. As the photon explores both possibilities, the phases associated with each path diverge. When the photon attempts to recombine and interfere with itself, this phase mismatch weakens the interference. If the difference grows too large, the interference can disappear entirely. Collapse would seem to arrive, not because of observation, but because gravity has forced the possibilities to lose their coordination. The same principle applies to entangled particles. When two photons share a single quantum state, they are bound by phase relationships that define their connection. If one photon climbs higher into weaker gravity, while the other remains lower, gravitational time dilation acts like a slow twisting motion that pulls their phases apart. The universe attempts to separate their stories. If the twist becomes too great, the entanglement may crumble. Gravity would then act as a barrier to maintaining quantum coherence over large distances or strong gravitational gradients. This is not only a theoretical concept. Experiments have begun to show hints of it. In research involving entangled photons sent between ground stations and satellites orbiting Earth, scientists tracked how long the delicate correlations survive. Though the results still support entanglement at impressive distances, there are subtle discrepancies and phase shifts that suggest gravity is influencing the quantum connection. The tests are not yet sensitive enough to declare a conclusion, but the direction is clear. Gravity and quantum information are not strangers. They already interact, perhaps more deeply than we expected. To push the investigation further, researchers have proposed quantum experiments in free fall. If particles are allowed to float in microgravity, such as aboard the International Space Station, the gravitational time differences across superposed paths become minimal. Quantum coherence should then last longer. If experiments confirm this, they will show that gravity's constant pull on time is one of the invisible hands that tear apart superpositions. The situation becomes even more intriguing near massive bodies like neutron stars or black holes. There, gravity can stretch time so violently that a single moment for a hovering observer might correspond to many moments far away. If a photon were ever placed into a superposition that straddles two significantly different gravitational heights near such an object, the phase divergence would be extreme. Collapse would come quickly. The wave function would not survive long enough to display interference. Gravity would force a choice almost instantly. This raises the possibility that the universe naturally suppresses quantum behavior near strong gravitational fields. The closer one travels toward places where space-time curves sharply, the harder it becomes for delicate quantum states to survive. Quantum strangeness might be a luxury of gentle gravitational landscapes. Near the monstrous hearts of collapsed stars, general relativity may crush uncertainty beneath the weight of curvature. There is a poetic symmetry in this. The more intense gravity becomes, the more it constrains possibility. The more the cosmos bends, the more reality must stiffen to remain consistent. Quantum freedom seems greatest where gravity is weakest. Light streaking through interstellar emptiness can remain a wave of possibility for millions of years. The same light skimming the edge of a black hole may forget it was ever uncertain. If gravity and time dilation can degrade coherence, does that mean collapse itself is purely a matter of timing? Maybe superposition lasts until time differences grow so large that the universe can no longer stitch the phases together. Collapse would then be a tug-of-war between quantum connection and gravitational separation. The clock becomes a judge. When the ticking between two branches of the wave function falls too far out of sync, only one branch can continue. This viewpoint offers a gentle alternative to Penrose's idea. Instead of gravity forcing collapse suddenly, gravity causes quantum states to drift apart in time until interference becomes impossible. Collapse appears because coherence quietly dissolves. The result is the same, but the story differs. Collapse is peaceful erosion rather than decisive enforcement. The truth may lie somewhere between these extremes. Gravity might both distort time and demand consistent geometry. First, decoherence weakens the ties between possibilities. Then collapse settles the final outcome. One process removes interference, the other eliminates ambiguity. Both play roles in the quantum to classical transition. Still, even if gravitational time dilation only affects coherence, its influence is universal. Every photon that moves through space experiences time differently depending on its path. No superposition can escape the grip of space-time. Light is therefore a perfect window into the subtle struggle between quantum information and gravitational power. The more we learn about this struggle, the more the universe begins to look like a place where the small and the large are already entangled in ways we barely understand. Quantum mechanics holds the keys to possibility. Gravity holds the keys to reality. Time, stretched and squeezed by curvature, may be the bridge between them. A photon does not merely travel, it ages differently along each possible path. That tiny difference in age can decide whether interference survives or collapses. The universe whispers that nothing moves through space-time without leaving part of itself behind, even when that part is its rhythm in time. In that rhythm, the quantum story may find its turning point. Light reveals the mysteries of time by how it refuses or fails to stay in step with itself. And when quantum coherence falters, gravity stands ready to decide the truth. Light does not simply cross space as if space were an invisible hallway. Space itself is shaped by gravity, and the photon must navigate the bends and curves written into the universe. Every star, every planet, every gathering of matter presses on the fabric of reality, and reshapes the routes available to light. Even when a photon seems to take a straight path, that path is only straight relative to a geometry sculpted by mass and energy. In this curved environment, the photon does not merely travel. It explores. It responds. It adapts to a landscape we cannot see without careful study. This becomes most apparent through a phenomenon known as gravitational lensing. When light from a distant galaxy passes near a massive cluster of matter, its path bends in a gentle arc. Observers on Earth may see multiple images of the same galaxy, each arriving from a different direction. The photons that create those images have traveled along paths separated by unimaginable distances. Yet the wave nature of quantum mechanics suggests that a single photon could in principle explore both routes until the universe forces a choice. In the grand interferometer of the cosmos, the photon wave function may stretch across paths that diverge by many light years. So why do we not see interference fringes stretched across the night sky? If a single photon can take multiple paths around a cluster of galaxies, why does it not produce a cosmic double-opening pattern on our telescopes? The answer lies in the role gravity plays in shaping time. Each path through curved spacetime has a different duration. A different rhythm of quantum phase unfolds along each route. By the time the photon arrives, those differences have grown so large that interference cannot survive. The wave function remains mathematically possible, but the universe has already ensured that the branches cannot meaningfully combine. Gravity, through time dilation, dissolves the coherence silently long before the photon reaches us. Even so, physicists have not given up searching for quantum interference in curved spacetime. They build interferometers on Earth that stretch as far as possible. They send photons through paths at different heights to expose them to different gravitational pulls. They construct long optical fibers, mountain to valley, to extend the phase difference that gravity might impose. Though the interference persists in many experiments, the edges sometimes soften. Tiny mismatches emerge. These early hints suggest that gravity may nibble at coherence even in gentle regimes. The cosmos itself may provide the most ambitious interferometer imaginable. Light can take several possible routes when it travels through regions filled with massive structures like galaxies and clusters. Yet by the time that light reaches us, the universe has already written the final answer. The different routes do not arrive with the same quantum voice. Phase differences stretch too far. Each photon appears to have chosen one path, even if its wave function once entertained more. The decision has already happened, hidden long before detection. Curvature becomes the judge, selecting which possibility emerges as truth. This interplay becomes even more dramatic near compact objects like white dwarfs, neutron stars, and black holes. There, gravity is no gentle gradient. It is a steep descent. Time near such objects slows so much that the phase of light changes rapidly as it approaches. If a superposition places a photon simultaneously near and far from intense curvature, the difference in its temporal evolution could become immense. The waves that once overlapped perfectly and produced interference may break apart, like an orchestra losing its conductor. The closer the paths come to a region of extreme curvature, the faster coherence fades. Scientists are beginning to aim quantum experiments toward these environments. They imagine observatories that might send entangled photons past the strong gravity of a nearby galaxy, while their partners remain in quieter spacetime. If the correlations weaken or collapse occurs more quickly than expected, gravity will have spoken. But these experiments remain in dreaming stages because they demand engineering sophistication we do not yet possess. Still, dreams often become the first step toward discovery. Closer to home, we explore the interaction between quantum behavior and curvature using light that we manipulate directly. Very long baseline interferometry links telescopes separated by thousands of kilometers. These telescopes collect light from distant quasars and recombine it to produce interference patterns sharp enough to resolve details finer than any single telescope could see alone. The wave nature of light survives that great span, proving that coherence can endure along enormous paths under Earth's gravity. Yet the fact that such experiments require careful calibration of timing and phase shows how easily gravitational influences could disrupt the harmony. The relationship between interference and curvature challenges us to ask what is truly fundamental. When interference fades, does the wave function collapse? Or does the wave function continue evolving silently while the universe hides its quantum roots beyond our reach? Is collapse a real shift or merely a loss of visibility? Gravity may provide clues, but even it does not yield them easily. To understand further, we can imagine a photon splitting into two possibilities near a massive planet. One part of the wave function skims close to the surface where time slows slightly. The other part travels farther away, where time flows more freely. The two halves drift apart in phase, and if they later attempt to recombine, the difference can wash out interference. Collapse may appear to have happened, though no explicit interaction occurred. Curved space-time itself might be enough to rob the universe of uncertainty. This leads to a question that sits at the heart of modern physics. Can space-time itself act as an environment that causes decoherence? If the answer is yes, then every photon is constantly entangling with the geometry around it. Every wave function is leaking information into the curvature of the cosmos. Collapse becomes a consequence of the universe recording too much about each possibility. Geometry remembers the difference between paths long after we have lost the ability to see interference. Alternatively, if space-time can exist in a superposition of shapes, then wave functions might survive even in strong curvature. Collapse would then require a different explanation entirely. The universe would be far stranger than we imagine, capable of holding multiple geometries in ghostly overlap until something, maybe gravity, or maybe something else, forces unity. Light is the perfect ambassador for investigating these possibilities. It slips through regions where gravity rules with iron certainty and also floats across places where curvature fades almost to nothing. It carries information across the longest distances known. It remembers everywhere it might have been through the phase etched in its wave function. When coherence survives, we learn how far quantum mechanics reaches. When coherence fails, we learn what gravity refuses to permit. A photon traveling from a distant galaxy may begin its journey as a whisper of possibility, its wave function stretching through multiple routes. But as space-time presses its demands, most of those possibilities fall away. When the photon finally arrives at our instruments, it tells a story. It tells us that the universe narrowed its future. It tells us that geometry guided its truth. The guiding question continues to deepen. Does gravity collapse the wave function, or does gravity simply stretch time in ways that erase coherence? Is the photon's collapse a decree or an erosion? Are we seeing the death of possibility, or merely the quiet silencing of quantum voice? Light keeps the answer hidden in the phase we often cannot detect. We stare upward through telescopes that gather ancient light. Behind each pinpoint glimmer lies a history of negotiation between the quantum and the cosmic. Interference and curvature argue silently. Only one path remains visible. The universe does not reveal how it reached that decision, but it shows us the result with absolute certainty. The night sky is a map of outcomes chosen long ago. Light has traveled through geometries that allowed possibility only until gravity declared enough. And every star we see speaks the same message. The wave function may begin wide and hopeful, but the universe itself decides where the photon will end. The most profound questions in physics often drift among theories and stars, far beyond the reach of human hands. But there comes a moment when thought alone is not enough. Hypotheses must be tested. If gravity truly influences quantum collapse, the laboratory must become a place where the smallest quanta feel the pull of space-time in measurable ways. Scientists now attempt to take what has been philosophy and turn it into experiment. The difficulty is immediate. Gravity is weak, astonishingly weak compared to every other force we know. A small magnet can lift a paperclip even though the entire planet pulls downward. To measure the gravitational field of a single photon or a tiny group of particles, we need instruments that are delicate to the point of impossibility. Yet every year, engineers create devices that push the limits one step farther. Computers grow quieter, lasers grow steadier, detectors grow more sensitive. The whisper of gravity may soon be loud enough to hear. One promising line of investigation asks whether gravity itself can carry quantum information. If gravity is a quantum force, then two tiny masses placed into superposition might be able to become entangled only through their mutual gravitational pull. If such entanglement appears, gravity must share the same quantum structure as light and electrons. On the other hand, if gravity cannot entangle and instead destroys superposition, collapse will reveal itself. This single experiment would answer questions that have resisted a century of speculation. To explore this idea, researchers attempt something that once sounded like science fiction. They cool small spheres of matter to near absolute zero, then levitate them in vacuum so they float free from vibration. They then try to place each sphere into a quantum superposition, such that it occupies two positions at once. If the gravitational fields of the two spheres weave together quantum mechanically, a measurable entanglement should appear. If gravity instead acts like a classical field that refuses uncertainty, the spheres will collapse back into definite form. Either outcome changes the future of physics. Another approach focuses directly on light. Scientists shine photons into interferometers that are stretched as long as human construction allows. The paths differ in height, so that gravity affects the photon differently, depending on the route. If collapse occurs faster, near stronger curvature, the interference pattern should wash out more quickly when the paths experience greater gravitational time dilation. Small signals have already emerged in experiments aboard high-altitude balloons and spacecraft. The results do not yet prove gravitational collapse, but they show that gravity matters to quantum coherence, even in gentle conditions. There is also a new frontier rising above our heads. Satellites and stations orbiting Earth provide platforms where gravity is weaker and environmental disruption is lower. Quantum communication experiments already send entangled photons from ground to orbit, proving that coherence can survive across the boundary between Earth's gravity and the near vacuum of space. Soon, more ambitious missions will attempt to place one photon in orbit while keeping its partner on the ground, then measure how long their entanglement persists. If gravity disrupts the connection faster than theoretical limits predict, collapse may be speaking in the language of lost correlations. Some dream even bigger. They imagine quantum payloads placed into trajectories that skim near Earth's surface and then arc far above it. Along this passage, the pull of gravity shifts dramatically. If collapse is tied to gravitational potential, the path might reveal a critical threshold where superposition becomes unsustainable. Light would begin its journey with many possibilities and end with only one, confirming that geometry has become the decision maker. These experiments must also contend with decoherence. The environment constantly tries to erase quantum behavior. Stray photons, heat from distant stars, and even the gentle sway of a satellite can collapse superpositions before gravity ever exerts its influence. To see gravitational collapse, researchers must remove all other causes, isolating gravity as the only remaining force capable of ending quantum freedom. Achieving this isolation is like asking the universe to stay perfectly still while we listen for its smallest secret. There is another difficulty. If gravity enforces collapse only when differences in curvature become large enough, laboratory experiments may never meet that threshold. Photons and small masses carry too little energy to bend space-time dramatically. The collapse may occur so slowly that decoherence masks the effect. In that case, we must look to the cosmos for answers. Massive stars, black holes, and clusters of galaxies are natural laboratories where light must confront extreme curvature. By studying how interference behaves across astronomical distances, we might glimpse the silent hand of gravitational collapse. Even so, Scientists persist in the lab. They build vacuum chambers the size of buildings to keep particles untouched by air. They create laser traps that suspend atoms like beads of light. They integrate superconducting devices that can record the faintest change in position or phase. Every advancement sharpens the tools needed to reveal whether gravity is a quiet partner in quantum collapse. The dream is not only to confirm or deny Penrose's hypothesis. The dream is to watch the moment when quantum uncertainty yields to gravitational certainty, to capture collapse in action, to see the universe transition from possibility into reality with the guidance of curvature. If such an observation becomes possible, we will witness the very rule nature uses to decide the truth. This scientific journey is not quick. It stretches across decades and continents. It demands patience and a willingness to test ideas that once existed only in thought experiments. But the stakes could not be greater. If gravity causes collapse, we gain a foothold toward a unified description of all physics. If gravity does not, then we must search for another thread that ties quantum behavior to the structure of space and time. Either result redefines our understanding. Light remains our ally in this exploration, for the photon is both simple and profound. It carries energy that curves space-time and phase that reveals coherence. It travels through every environment from the laboratory bench to the edge of black holes. It is the perfect witness to how the universe enforces its laws. One day soon, a photon in a carefully crafted experiment will make a choice that tells us whether gravity whispered that decision into being. When that moment arrives, we will no longer ask whether collapse is triggered by measurement, or consciousness, or accident. We will understand that nature itself decides when possibility ends. If gravity is the hand that pushes quantum possibility into definite reality, then the entire architecture of physics must shift to acknowledge that fact. The implications stretch far beyond the behavior of a single photon. They reach into the nature of information, the limits of communication, and the boundaries of what the universe allows. Every collapse would become a moment where space-time asserts itself over uncertainty. Every path a photon abandons would mark a geometry that the universe refused to inhabit. To see how profound this shift would be, imagine a long-distance quantum interference experiment stretched across the cosmos. Two possible photon paths weave through regions where gravity differs. If gravitational collapse is real, then there is a maximum distance over which quantum superposition can survive. Past that limit, the photon wave function would lose all ability to maintain coherence. The interference that lies at the heart of quantum communication would evaporate. The universe becomes a judge not only of truth, but of connectivity. There would be a horizon beyond which quantum behavior can no longer reach. This would impose a fundamental boundary on how far future civilizations could send perfectly secure quantum signals. Entanglement would not survive arbitrary distances. The dream of a galaxy-wide quantum network, immune to eavesdropping and convolution, might be constrained by curvature itself. Perhaps no matter how advanced a species becomes, the universe ensures that quantum unity cannot stretch farther than gravity allows. Such a rule would reshape how we imagine the future of exploration. We like to assume that technology marches forward without limit, but physics often places quiet walls that cannot be crossed. If gravity collapses light at certain thresholds, those thresholds would define a map of what is possible. The highest mountains in science are not made of rock. They are built from the principles the universe refuses to bend. Another consequence emerges when we consider entanglement near massive objects. If entangled photons stray into regions with strong gravitational gradients, their link may crumble more easily than decoherence alone predicts. Gravity could split their shared identity, forcing each photon into a local truth. This means quantum behavior would depend not only on distance, but on the shape of space-time between them. Communication through entanglement would remain strong in soft curvatures, but falter where gravity grows fierce. This has already inspired ideas for new experiments. Researchers propose sending entangled photons near Earth's surface, while keeping their partners high above. They want to find the exact gravitational difference at which collapse begins to affect correlations. If that threshold can be measured, it would mark the first quantitative fingerprint of gravitational collapse. We would not be guessing anymore. We would be listening to what gravity tells the quantum world. Light traveling near black holes raises an even deeper question. When the gravitational field becomes extreme, time dilates to such a degree that even the ordering of events can become uncertain. If a photon in superposition tries to survive that environment, collapse may be so rapid that quantum behavior is snuffed out before it begins. The wave function would collapse long before we could detect interference. The universe would enforce singular reality in places where geometry approaches the limits of its own structure. Some theories suggest that information falling into a black hole is preserved in subtle correlations at the horizon. These correlations are thought to be quantum in nature. If gravity collapses wave functions near such horizons, the flow of information might shift dramatically. The balance between quantum behavior and curvature would determine whether black holes erase quantum structure or store it in forms we struggle to decode. This reveals a fascinating tension. Our deepest puzzles about black holes center on whether information is lost or preserved. Collapse induced by gravity could offer a new perspective on how information flows when space-time is pushed to extremes. Collapse might become the mechanism that stamps information into the geometry itself. Every photon absorbed by a black hole would collapse into a single story. The abandoned possibilities would vanish because the immense curvature cannot sustain multiple futures. We must also confront the relationship between collapse and entropy. When collapse chooses a specific outcome, the wave function's spread collapses into a narrower state. If gravity drives this, the direction of collapse might contribute to the arrow of time. Time flows forward not just because entropy increases, but because collapse prevents the universe from revisiting superposed pasts. History gains direction because gravity refuses to let possibilities remain open forever. Perhaps then, the classical world is not a separate realm emerging spontaneously out of quantum mechanics. It may instead be a continuous enforcement by gravity. Classical behavior would be the ultimate outcome of many collapses, each removing uncertainty piece by piece until the universe displays a firm reality. This would explain why objects as large as planets and creatures and minds feel inexorably classical. Collapse happens constantly at their scale because gravity makes their quantum alternatives impossible to maintain. There is a subtle beauty in this idea. The same law that shapes galaxies might also sculpt truth for the tiniest quanta. The cosmos would not operate under separate rules for different sizes. The universe would be one story told with the same voice in every chapter. Collapse becomes the punctuation that keeps the story legible. Gravity becomes the editor that ensures no contradictions survive. The transformation extends even into philosophy. If collapse comes from gravity, then reality does not depend on observation. Existence does not wait for us to notice. The universe decides outcomes for itself. Consciousness becomes a reader, not the author. We do not choose what is real. We discover what has already been chosen. Yet this raises one final question that cuts to the marrow of physics. If gravity collapses wave functions, where exactly is the line? How fragile must a quantum state be before gravity enforces its rule? How far can possibility stretch before geometry demands a single answer? Is the boundary sharp or soft? Does it shift based on context? Perhaps the universe never draws a perfect line. Perhaps collapse is a spectrum. Superposition fades gradually until nothing remains but certainty. Even if that is true, the search for the tipping point remains the key to unlocking the mystery. The collapse boundary is the doorway to a theory of quantum gravity. When we find it, we will know where probability bows to curvature. We will know where the smallest particles meet the heaviest questions. Light has always revealed the universe to us. But if gravity collapses light, then light also reveals how the universe decides what can and what cannot be real. Every photon that strikes our detectors carries the answer already locked into its fate. And when we finally understand that fate, we will see not just the cosmos around us, but the rule that shapes truth itself. Light reveals the world to us, yet its own nature remains hidden behind a curtain of probability. A photon can explore many paths at once until something forces a decision. For more than a century, physicists have argued over what causes that decision. Some say collapse is only in our minds. Some say the universe splits into countless unseen branches. Others insist collapse is a real physical event. And now a bold idea suggests that collapse may be written into the geometry of space-time itself. Gravity, the shaper of stars and keeper of cosmic order, may also be the rule that chooses which possibilities become truth. This idea brings our understanding of the universe to a crossroads. On one road stands the quantum world of uncertainty, where probability reigns and nothing is real until observed. On the other road stands general relativity, where space-time curves with confidence and events unfold in a single decisive reality. Each road works perfectly within its own domain, yet neither can handle the full scope of existence. When the smallest particles fall under the influence of the heaviest questions, both theories hesitate. Gravity does not know how to bend around maybes. Quantum mechanics does not know how to collapse into geometry. Somewhere between them must lie the rule that all of nature obeys. Light has been our guide through this puzzle, because photons are both the simplest quanta and the most cosmic travelers. They move at the very speed limit of the universe. They carry energy and information across unimaginable distances. They are influenced by gravity, and they in turn influence gravity through the energy they bear. A photon in superposition drags multiple possible curvatures behind it, like shadows. The universe cannot allow those shadows to grow without consequence. If gravity enforces collapse, then every photon's landing on a screen becomes the moment when space-time makes up its mind. The wave function no longer fails at random. It is forced by geometry to choose a single history. The classical world emerges because gravity does not permit the cosmos to fracture into inconsistent forms. Light shows this truth in every interference experiment. As long as the possible paths remain closely similar in gravitational consequence, interference thrives. When the differences widen, coherence dissolves, collapse follows, curvature chooses. If this is the final answer, then quantum mechanics is not a puzzle of observation. It is a puzzle of structure. The collapse boundary would depend on mass energy and space. It would depend on how time flows differently along different possibilities. It would depend on whether space-time can remain flexible enough to hold multiple geometries in suspension. Collapse would then be a physical law as real as the speed of light or the attraction of gravity. A photon would not collapse because we looked at it. A photon would collapse because the universe refused to host two different shapes of itself at the same time. But perhaps gravity does not collapse anything at all. Perhaps space-time can exist in superposition, just like photons and atoms. Collapse might be only an illusion caused by decoherence. The universe could hold infinite branches of possibility, each one evolving quietly. The world we see would be a narrow thread through a vast forest of outcomes. The truth would then be richer than we can comprehend. Gravity would join the dance of uncertainty, and collapse would become nothing more than a practical limitation of our perception. There is also a deeper possibility that both views are partly correct. Decoherence might weaken quantum states by spreading information through spacetime. Gravity might then enforce the final decision when the curvature difference reaches a threshold. Collapse would not be a sudden magical command, but a process. A gradual narrowing of possibility until reality can hold only one form. Light would fade from superposition into certainty, step by step, across distance and time. What makes this question so extraordinary is that the answer will change the structure of physics. If gravity causes collapse, then our universe is one singular story, and quantum mechanics must adapt. If gravity does not cause collapse, then space-time itself must be rewritten as a quantum object where certainty is never guaranteed. Either outcome reshapes the foundation of science. Either outcome brings us closer to a unified understanding where the small and the large obey the same profound rules. This book has followed the journey of light from wave to possibility to collapse. We have watched how a photon can slip through two openings at once and later arrive in a single point on a screen. We have seen how time dilation can pull superpositions apart. We have looked at experiments on Earth and dreams of experiments among the stars. Each step invites the same question: what decides when reality stops being a maybe? And although the answer is not yet known, the pursuit of it has already revealed something powerful. The universe is not divided into separate realms where different laws battle for control. The universe is one continuous reality where every event is linked to the geometry of space and the flow of time. Quantum mechanics and gravity are not enemies. They are two parts of a truth still forming. Light shows us the gap between them, and gravity may be the missing bridge. One day, a photon in a carefully prepared experiment will refuse to interfere. It will collapse at a moment predicted not by chance, but by gravitational calculation. Or it will defy collapse altogether and remain coherent even when gravity demands otherwise. In either case, the universe will have spoken. The mystery will step from the shadows into understanding. Until that day, every photon that reaches us from a distant star is a messenger. It tells us that possibility once existed, and then something chose. It carries the decision the universe made on its behalf. It is a reminder that the cosmos is not merely observed, it is resolved. Every glimmer in the sky began as a superposition. Every glimmer arrived as a truth. Light reveals everything except the rule that decides when possibility becomes reality. We stand on the edge of that revelation. And when at last we discover whether gravity collapses the wave function, we will know not only how the universe behaves, but how the universe chooses to be real.